Hi friends, today we're going to talk about this Pinterest paper just out of the KDD 2025 OmniSage. It's an effort to build universal embedding by taming different types of data, graph data, sequence data, and content features. It is not only different data types, but also different modeling architecture. It aims to leverage efforts of its predecessors, PinSage, Pinterformer, and Pixie. So let's get started. So OmniSage's goal is to provide universal embeddings for their entities such as pins and boards. If you have read Pinterest papers before, they already have some in-house modeling. So graph neural networks such as PinnerSage. They also have their in-house sequence models such as Pinterformer. And for content-based models, I'm not sure they have any published papers, but apparently these days, you can also call some open source models to get the content embeddings, including text embeddings and visual embeddings. These three different modeling techniques use different training data preprocessing. For example, the graph neural network method usually need to use the graph neighbors as input data. And for Pinterformer representative sequence models, you need to process your data in a sequential way. And content models, it needs pixels and text tokens. So essentially, OmniSage wants to leverage these different data types and training techniques to provide a universal embedding for pins and boards. So their proposal is that they want to use multitask learning. So for example here, for the entity-to-entity task, they will use the graph neighbors to provide positive and negative samples. And for the user entity task, they can reuse their work in Pinterformer and sequence model. And for the entity-to-feature task, they can take care of the content embeddings. Essentially, three types of data, three types of tasks. So what is a graph? Graph is something that contains both engagement data and categorical data. Like two pins can have edges because a user clicked one pin because another pin. So this is called engagement kind of edges. And also you have categorical edges. For example, this pin is saved in this board. In Pinterest example, the graph has two types of entities. One is pin, the other is board. They also have two types of edges. One is engagement based, the other is categorical based. So with the graph field, they are able to do the neighbor sampling to generate the graph neighbors for each entity. They do this via the random walk with restart. The paper specifically highlights the challenge that it is a heterogeneous graph. So here is different edge types. What they do is that across all the different relations, different edge types, they choose the set of the relations and then get the subgraph. This is saying that they want to get the graph neighbors for this node U, and when look at edges, we only look at a subset of edges where the edge type belongs to R. This will get all the graph neighbors where they form edges only within the edge type R. Essentially, they will look into all the edge sites and get the union of edge types. So as you can see here, they define subsize of edge types R1, R2 to Rn, and eventually they will union all the edge type subsets. This can be beneficial and actually requires a lot of customization and business logic understanding because you really need to experiment like what kind of edge types goes better together in one subsets and what edge types are not better together in the same subsets. But essentially after graph sampling, for each node, you should have a list of graph neighbors. But how are those graph neighbors used? The biggest innovation in this paper is their usage for graph neighbors. So when you look at this image, it's when they're trying to encode embeddings for a pin or for a board. They not only take the content features, the text features, and image features of that target, they also look at the features from the graph neighbors. For example, this is the target pin. If you look at the neighbor pins and neighbor boards, content features as well. And after they gather the common feature of the target and its graph neighbors, it will pass through a transformer to aggregate. And after that, pass through an embedding layer. And after that, pass through MLP and L2 norm to output the final embedding for that target. Essentially, instead of training another GNN, they are only using the graph neighbors and use transformer encoder to do the aggregation instead of using GNN. Next, let's talk about the entity-to-entity task. The entity-to-entity task measures the similarity of two embeddings. It is used to supervise two goals. One is the similarity of a node and its sampled nodes. Basically, the distance between one node and its graph neighbors must be close. The second supervision goal is for the engagement data. If there's engagement data pairs of ping and board and pings, their embeddings should be close, and then those who are not engaged together. Essentially, for any tasks, we want the universal embedding to pull the nodes closer to its graph neighbors and also closer to the co-engaged entities. The second task is entity-to-feature task. Their intuition is that they want to make sure that the common embedding information are preserved in their output embedding, which is this one. So they categorize the input feature into several types. And for each type of input feature, they let it pass through a MLP encoder, which is called GXU. And then they compare this GXU with the output embedding. So this is a positive example. And for a negative example, they just randomly sample entities of the same type. They argue that in this way, the content input features are well preserved in their output universal embedding. And lastly, the user entity task. This is the sequence modeling component of the OmniSage. They basically leverage a lot of their previous work in PinnerSage. First of all, they use user previously engaged pins to represent and generate a user embedding. And then they have two goals. One objective, as they said, is the next action loss. So given the user current sequence, you predict the next sequence. So given the user current engaged entities, you want to predict what are the next pin that the user will engage. And second one is a future action loss. So here is not necessarily the exact next action. It can be exact next t plus k action. This is the similar action. This is a similar setup. So these objectives keeps track of the sequence modeling. This objective models user sequence action. So the overall objective of this multitask learning is that they have the entity-to-entity loss, they have the content feature loss, and then they have the sequence modeling loss. Each loss component had their own weight, and they tune the weight for the eventual loss. In terms of tuning techniques, they talk about two of their innovations. First of all is what they call the graph engine for heterogeneous graph. If you have read the Pixie paper, this might sound familiar. Essentially, they have a neighbor sampler that is implemented using C++, supposed to be highly efficient. And secondly, they use RockDB to implement their feature riser so that they can fetch features on the fly, which I imagine could be at a batch training time. And second innovation, what they said is their chunked sampled softmax loss. It's a trade-off between space and time. So what they're doing is that they partition the giant matrix into smaller chunks and then do a for loop so that instead of calculating the outer product of three giant matrix, they're calculating per chunk. It might take slightly longer, but it will have less memory pressure. It might actually be faster if your chunk is small enough and other products is faster enough for smaller chunks. In terms of evaluation, first of all, they did offline evaluation by constructing their own evaluation data set. As we just talked about, in training, you provided those positive and negative examples at training. So at evaluation time, they constructed a new data set so that they can calculate the recall at 10. And what they're saying is that OmniSage is better than both PinSage and PinReformer. PinSage was previously used for entity-to-entity objectives, and PinReformer is sequence modeling in Pinterest that is suited for the Go user-to-entity task. They also did some ablation tests so that we can derive learning from. This comparison is saying that they found that adding the graph neighbors actually provide better results. And here, what they're saying is that multitask learning is better than single task, which makes sense. And here they also explore different edge count because one of the more expensive procedure here is a random walk, the graph sampling. They are saying that actually, and from this table, we can see as you increase the number of edges, you don't observe that significant improvement. And it is some trade-off that they are posing here. There are also some interesting ablation tests in their appendix if you look at the aggregation technique evaluation. One of the key innovations that they mentioned here is that instead of training a graph neural network like graph attention, what they're doing is that they package the graph neighbors as a sequence data and then pass it through transformer encoders. They're saying that their new approach to replace the graph neural network is actually a better way to do feature aggregation. The performance drop when they replace their original transformer-based approach with the graph neural network. So that actually is also makes sense because transformer is a much more complex architecture compared to GAT. And I think this is the main innovation of this paper of not using GAT to process the graph neighbors, but rather package the graph neighbors as sequence and use transformer encoder as aggregation instead of graph neural network. Another just technique we can learn from them is that what they're saying is that using random negative is much better than using batch negative samples. So I see also like with more random negative samples, it will provide much better results. So that's it for the OmniSage paper. My biggest takeaway is that instead of training a graph neural network, they pass the graph neighbors using transformer-based encoder. In this way, they show the best of both worlds. They both use transformer-based architecture, but also leverage graph data. And hope you enjoy this, and thank you for watching.